I'm going to get things underway here with today's webinar, which is Leading the Way in Simulation-Driven Machine and Line Design. And I'm very happy. My name is Dr. Philip Glennie. I'm the Director of Marketing and Sales here at Long-Term Technology Services. We're a Siemens certified smart partner and technology partner. And I'm joined here today by Bernd Moosman, Executive Portfolio Development Manager at Siemens Digital Industries Software, as well as Xiaozhang Shi, the Director of Industry Application at Siemens Digital Industries Software. We're very, very grateful today to have Bernd joining us from Germany and Xiaozhang joining us from California. At least that's where I think you are. Xiaozhang, are you in California right now?
Yes, I'm in California. Thank you.
That's right. Here's a little quick note on today's agenda. We've got the introduction followed by Welcome to Mechatronic Engineering, which is when Xiaozhang and Bernd will take control and tell you some things about next generation approaches here to mechatronics engineering. Then we'll follow that with some real case studies, some real success stories, and then followed by a quick Q&A. And so with that, I'm just going to flip off my camera now just to avoid distracting here. Just bear with me one moment. And so now that I've done that, I will reshare the presentation. And again, there's the little lag. There we go. And so, let's start off with a little bit of an introduction here to introducing some digital twinning solutions. First is a little bit about us at LTS. We are very proud to co-host this webinar with Siemens. Here at LTS, we really like to think of ourselves as a trusted digital partner for exploring new solutions that are going to help lower your costs, lower your lead times, especially with the respect to today's topic, increase your production quality and efficiency, and at the end of the day, really just make your company more profitable and competitive. And we're looking to do this at two levels. The first is that more long-term level, if I can use the phrase, which we would do by helping you build really a common digital thread through a number of industry solutions that can span from your product design and engineering to your production scheduling, your plant management, and your machine and line design and commissioning. And that last one is what we're going to be talking about today. But we also understand, because we work with a lot of small to medium-sized businesses, we realize that when it comes to these large, digital industry solutions, we understand that we need to really meet companies where they are. And so if there's anything you see in this webinar that seems like it's kind of like overkill, too much upfront investment of time, I just want you to know that at LTS as partners, that's really our responsibility to create situations that work for you and give you that really clear ROI. And just as importantly, a very compressed payback period. Making sure that on these investments, you get your money back very, very quickly and that you move forward with these investments much stronger than you were before. And we do that through a combination of software, training, and consulting that's tailored to your exact needs. Before I go on, I do want to say be sure to join us for our next webinar, which is bringing the human into your process planning. So this is going to be a webinar about using digital human models to optimize and standardize your ergonomic practices for maximum safety and efficiency. And for this one, we're going to be joined by global experts Allison Stevens, who helped Ford Motors build its global ergonomics program, and Karen Baynar, who's an expert on digital human modeling software with Siemens. Today, though, we're going to focus on how using a single virtual model for your electrical, mechanical, and automation engineering can really change the way you build machines and production lines. So here's some key trends that I like to go over before each webinar, just to help contextualize what you're about to see. As many of you know, there's a number of trends that are forcing companies to become leaner, smarter, and more agile, while somehow increasing the quality of their products. And some of those trends are what you see listed here, right? You're talking about consumer-driven customization, smart machines, which is going to be particularly relevant to today's hyper-automation, global competition. At the end of the day, the easiest way to say it is that customers want it all. They want more personalized, they want more complex, faster, with higher quality. So basically the question is, with shrinking lead times, how do you create better, more complex machines and products? And we believe that the holistic digital twin is the way to meet these trends and their accompanying demands. So a quick note, just a background on what we mean when we say digital twin. Basically, you can distinguish it from traditional simulation, where you're usually thinking of a geometric, maybe a kinematic simulation that's pretty hypothetical or theoretical in nature. A digital twin is really a virtual replica of your product or machine that gets into those realms that we're going to be talking about today, right? Your electrical engineering, mechatronic, automation engineering, using a physics-based engine, right? So you're incorporating the laws of physics. So let's say you're talking about a digital twin of a pick-and-place robot, right? If you speed that robot up too much, eventually the laws of physics are going to kick in and make that not feasible, but as you keep speeding it up. But just as important for this webinar really is bringing in that automation component as well, because these simulations can run from real PLC code, right, and be driven by real controllers. So you can generate and validate your PLC code from the same model that your mechanical and electrical engineers are using to validate their own designs. So now you're talking about a simulation that really is at the point now today where you're offering a stand-in for a real device. And you can also connect the digital twin to that real device in real time. And that has big implications for the way that we're going to do things in automation and manufacturing. It's this approach that really allows you to bring in more of your commissioning work into the design and engineering stages of your machine's life cycle. And you can do this by performing more work than ever before in that virtual setting. Again, bringing in that electrical behavior, bringing in that mechanical behavior, bringing in the PLC. And so as you do more of that upfront work, you know that you're going to have it error-free and save a lot of time and money when it comes to actual commissioning. And once you've really committed to going down this road of the digital twin, which we believe is just basically going to be an industry requirement in the near future if it hasn't become one already, but now it's a question of scope, right? And if you've been in any of our previous webinars, right, you've kind of seen us basically make our way down this funnel. We started out with our first webinar with full-scale plant simulation. We then moved into like the robotic cell and the production line. Today we're going to focus a bit more at the level of the individual machine. And we will talk a little bit about the production line, but we're going to really focus on the mechatronics concept design behind individual machines, as well as some of the automation programming behind those as well. And so this gives you a sense of where we are now. So now we're really in this tier for today. And with that, I would like to turn things over to Bernd and Xiaozhang to speak a little bit about the next generation approaches to mechatronic engineering that we're going to talk to today. And with that, I'll turn it over to you two.
All right. Thank you, Phil, for this nice introduction. Yes, my name is Bernd Mussmann from Germany, and I spent roughly 18 years right now in the automation, electrical engineering, and commissioning area. And in the past, I would have really loved to have tools like we have today. Yeah. And all right, Phil, then please start over with this small video, what we have seen here. All right. So, and on the left side, we really see our digital twin, and on the right side, we see the real machine. Of course, what we have done, we built up firstly the digital twin before we constructed the real machine. And this gives a lot of benefit to all our machine builders. And we will get a little bit more in detail in the next slides. So why we are doing that, Phil, please switch to the next one. Actually, we're doing that because simulation helps us to wipe out failures and brings us to a better level of quality. I think everybody knows the Sigma rule of quality, and which basically says, as early I find failures in my engineering, as more money I can save, because with each step later in development and commissioning or so on, I have an increased cost of 10. Yeah, and for example, if I find a failure in the electrical wiring diagrams, yeah, it's if I find that in an early phase, I can really wipe out that failure by 2-3 mouse clicks, right? And if I don't find this failure at the end, if I send my machine already on site and I have to commission this machine, I have to spend thousands of dollars to to wipe out this failure, because maybe I have put in the wrong variable speed drive, and so I need to build new components and so on. And I have really a lot of work to do to wipe out this failure. And this basically means as earlier as I find my failures, I increase even so my quality of engineering. So, and this leads us, of course, if you would switch to the next slide, Phil, to have a good process of tools which helps us through the engineering phase. If I'm on the machine building side, I commonly have my CAD geometries, and within the Mechatronics concept designer, the NX MCD, I really can bring my machine to life in an early engineering phase, and even so I can build up simple concepts of my machine, bring in ideas in a quite early phase, so that I can visualize it, and later on I can automate this machine with the automation designer and NX, and even so from the automation designer I can automatically generate I would say ECAD plans and PLC code for Siemens PLCs, and then I can put it into my real machine, and then I can look into, or I can basically do a closed loop virtual commissioning with the PLC code I've generated and the MCD at the end of the day. And I don't need all the tools to be on the road at the end of the day efficient. Yeah. So I with each tools here, I have a big benefit already. And today we will focus a little bit more on the MCD, as Phil already said. If you could switch to the next one, please. Yeah. Right now, let's get a little bit more detailed and a little bit more into the praxis or the real life world, I would say. If I see the machine here, I have a common door, and what I need for functionality to open a door and things like that, because this is a safety relevant machine, I have to monitor the situation of the door. Is the door closed or opened? Therefore, I have to add limit switches. I have to add safety relays, that if the door gets open through operation of the machine, that that really the load gets off of the machine, and the machine stops on the right side, so that no human gets hurt at the end of the day. Yeah, I have to build up the total control cabinet. I have to wire all these components I built in. I have to write the PLC code, and if I think about bigger machines, I maybe have to add actuators to support the opening and the closing of big doors. Yeah, and as we can see here, even simple functionalities at machines are very quickly getting very complex. If you would go a slide further, Phil, please. So how we see our MCD in the total engineering process. Yeah, if I start with the idea, then I commonly build up some blocks, and with these blocks I really can already build up a simple CAD model, a 3D model, and with this CAD model I can do I can kinemize this model and bring really life into the machine already. I can add signals and sequences in this phase. Yeah, and in this phase I can already evaluate my concept and look if I'm on the right way. Yeah, and if I've done that, I can reuse my information I've already added to my model in the virtual commissioning phase. Yeah. In the virtual commissioning phase, I add maybe some kinematics if I have robots, and even so I add already some sequences that everything works together. I add my virtual PLC controller, for example, to start programming my first PLC code on that line. And at the end, I really bring the total PLC code over to the real machine, and I'm on a big better position to do the real commissioning right away from the virtual commissioning. And now let's a little bit look into how that could look like. Yeah, where does the kinematics come from? Yeah, the kinematics come from, of course, the CAD model, and then we have a small tool which is called Animation Designer. Yeah, as a mechanical engineering, I'm quite often maybe use this tool already. And on the right side, we see that I just imported the CAD geometry or the 3D CAD data into the Animation Designer, and I can transform my constraints I have built in the modeling phase and design phase to kinematics for the robot, for example. Or I even can use the straight way to MCD, that I even import the total or that I load my model into MCD, and I start kinemizing my geometry. So if we would switch to the next slide, Phil, then I'm probably can get a little bit more precise for you. Yeah. Here, for example, we have 3 different kinds of mechanical solutions to which would fit to my machine, and which would fit to a solution which I want to reach. The base situation where I start from is the upper screen, and on the left side I see a solution, and on the right side I see a solution. And the task is that I have to optimize the cycle time of proving my bottles. Yeah, so I could do that with a revolver solution, or with an movable traverse, I would say, with a movable axis which moves up and down to which would fit to the right bottle size. Yeah, good. And what I have to do, I have to add actors and sensors. I have to create signals, and even to add sequences here to validate at the end my engineering solution. And if you would switch to the next or to the video, which should come up here, even you can see the task is even so that I have to increase the cycle time, and even I have to adapt my machine to the different bottle sizes. Yeah. So, and therefore, of course, the revolver solution wouldn't be good, because I have a lot of time to adjust the revolver if I would change the bottle size. Yeah? So certainly it would be better to have the solution on the right side, where the axis recognize the size of the bottle and then moves into the right position. Yeah? And this really shows how I can evaluate my solution in an early engineering phase. Building up such models, I would say 3-4 hours. Or Xiaoshang, what would you say? How long would you take for building up such models?
So, but thank you for showing this model. So normally for those kind of case, I would say around 3 to 4 hours. But one of the benefits that I also want to stress here is the knowledge and also the model can be reused when we build the second one. So those kind of the thing is the benefit of leveraging NX and MCD here. So yeah.
Right, absolutely. That's a pretty good thing. And even so, please recognize this is a fully physics-based simulation. Yeah, so you could interact with the model, and as you can see here, the bumpers are moving the bottles out of the line if the check is not good. Yeah, and this is really a fantastic solution on that. Yes, Philip, if you would switch to the next one, please. If we have, for example, also robot systems, yeah, then I even so can validate my machine how to interact with my robot system. Yeah? So the MCD has, I would say, a general kinematic for robot systems. It's not a specified KUKA or Yaskawa or ABB robot, which then when the robot behaves, it's really a generic kinematic, and you can evaluate if the robot can reach your working area, so that you can choose maybe a different robot if he is too small or something like that. And even you can check how the robot reaches or how the robot has to reach the work part he has to pick and place, and so on. All these things you can evaluate in a quite early phase, even without having a robot or controller or something like anything else on your hand. Yeah. If you would switch, please, to the next video, which we want to show here. Oh, all right, it's coming up. Yes, and here we want to show how quick a robot is being able to kinemize. Yeah, on the left side you have already the physics, and you have seen if I start the simulation, the robot has no behavior. Yeah, and with one click, and I can apply on this kinematics the inverse kinematic for the robot system. I add my tool center point here, and then I add different positions which the robot needs to reach. So then I can add a little bit, or I can modify my position, how the robot has to move to this position. Yes. So in this case, I say, okay, the robot has to move from the X side to the target point, and then he has to move to a second target point, even though from the X side. And here you already see how the robot can move. Yeah, and even so, you can have a look on the path how the tool center point has been worked. If we would go to the next video, please, Phil.